Alright, in this section here we're going to be talking about UFDs, or unique factorization domains, and Euclidean domains. A little bit about other types of domains as well, but these are the two we're going to really focus on. The first thing I want to do is I want to go over some definitions that I think we've seen at this point, but I want to make sure we have them before we start defining the domains that we're interested in. So let's begin by supposing that D is an integral domain. We say that one element A divides another element B if there's a solution to the equation AX is equal to B inside the domain we're looking at. Now, an element of the domain is said to be prime if it's non-zero, it's not a unit, and whenever it divides the product of two elements of the domain B times C, then it divides one or the other element individually. Either A divides B or A divides C. So this definition of prime for an arbitrary integral domain is a generalization of what's called Euclid's lemma for the normal integers. Now, a non-unit A in a domain is said to be irreducible over the domain if whenever you can write that element A as B times C, where B and C are other elements of the domain, then one of those elements has to be a unit. Now, the intuition behind irreducible elements is that whenever you multiply within an integral domain by a unit, that this is an invertible action, and so multiplying by a unit doesn't really alter fundamental properties of an element. So if an element is irreducible if really there's nothing else similar to it except for things that are off from it by a unit. Also, irreducible elements are really elements that can't be broken down further by multiplication within the domain. So in some ways they're like the building blocks of the irreducible domain. Now, inside the integers, as we've seen when we've seen the definitions of primes and irreducible before, we've seen that prime and irreducible are the same thing within the integers. However, when you move into an arbitrary integral domain D, the notions of prime and irreducible are not the same. What is true, however, is that an element which is prime inside any integral domain must be irreducible. And we can justify that pretty easily. So let's suppose that P is an element of an integral domain and suppose that it's prime. And let's show that it's irreducible. So let's write it as A times B, and let's show that one of A or B is a unit. Now, without loss, we have symmetry with our letters here. So we could assume that P divides A because P is prime. And what this means is that we can write A as P times X for some element X in the domain. When we go back to our original equation, P is AB, and substitute in, we find that P is Px times B. And inside an integral domain, we're allowed to cancel. So we can cancel the P's from both sides of that equation to find that 1 is X times B. And this means that B is a unit, and P is therefore irreducible. And it's the without loss of generality that gives us the statement either one of A or B is a unit. We broke our symmetry. If we would have chosen things the other way around, we would have concluded that A was a unit. Now, as I said before, inside the integers, the notions of prime and irreducible are the same, and inside certain types of domains, as we'll see later on, the notions of prime and irreducible are the same. However, it's very important to know and to see an example demonstrating that there are domains and elements of that domain that are irreducible but not prime. However, in order to do that, I'm going to need a little bit more machinery. I'm going to need something that's called a norm map. Here I am straying a little bit from chapter 18 of Gallian. He defines a norm map in one particular way, and I'm going to define it a little more generally. So let's take a ring R, which is the integers adjoining gamma, where gamma is a root of an irreducible polynomial of the form x squared plus ax plus b. Because I'm requiring this polynomial to be irreducible, what gamma is it could be a real root or an imaginary root. If it's a real root, it is not a rational root. And so, as we've seen before, gamma has a conjugate, which I'm going to denote by gamma bar. And playing around with the equation x squared plus ax plus b is equal to 0, you can find that this other root of the polynomial, gamma bar, is negative a minus gamma. That's also a root of this polynomial. And so what we do is we define a norm map. This is a map from our ring R to the natural numbers. And we get this by taking an arbitrary element of z adjoining gamma, which has the form w plus z gamma. And we take the absolute value of this element times its conjugate. So we take the element w plus z gamma and we multiply it by w plus z gamma bar. We take the absolute value of that to make sure that we're landing inside the natural numbers. And if you do a little bit of algebra and some symbol pushing in a dark room with some pencil and paper, you'll compute that this norm map is a little bit easier to remember as taking w squared, subtracting awz, and adding bz squared to it, and putting an absolute value right around there. Now, what your book does is it works with this sort of simplified example. It works only with polynomials of the form x squared plus b. So if d is a number that's bigger than 1, if it's not divisible by any square other than 1, we'll let it be divisible by 1 squared, then the square root of d is a root of what is an irreducible polynomial, x squared minus d. And then when we go back and plug in those particular values into the norm map that I have above, you find that the norm map on z adjoin the square root of d is w squared minus dz squared with absolute value signs around it, and this is what Galian defines as the norm map. So he only works with these simplified examples where a is 0 and where d happens to be not divisible by any square other than 1. And so this is what he gets as the norm map. Now, there are some properties of norm maps that are going to make them really useful for us. And the first property, perhaps the most important property, is that norm maps are multiplicative. So if we take two elements x and y in z adjoin gamma and we look at the norm of that product, then that's the norm of x times the norm of y for all x and y in z adjoin gamma. Now, other properties that are true of the norm map that are fairly easy to prove in the simplified example of Galian are that if you have an element x, its norm is 0 if and only if that element x is 0. The other map that's easy enough to, or the other fact that's easy enough to prove is that the norm of x is 1 if and only if x is a unit inside z adjoin gamma. So this is a really nice and convenient way to identify the units of the ring z adjoin gamma. And another thing that can be helpful to us is that if we take the norm of an element x inside z adjoin gamma and we happen to get a prime number, then it has to be the case that this x is irreducible inside the domain. One of the exercises I've given you in your homework is to show that you can have an irreducible element that does not have a norm which is prime. So you have to be careful here. Here we don't have an if and only if statement, we just have an if then statement. And what I would say is a good exercise is to go back and prove that all of these properties hold if you work in the sort of simplified example of Galian. If you look inside the ring z adjoin the square root of d, where d is not divisible by any square other than 1, then all of these properties are somewhat easy to prove. They're not so terribly difficult to prove in the general case as well, but things are a little bit cleaner when you work with this simplified example. Now, once we have the properties of a norm map, we can use them to come up with, fairly easily, an example of a domain where we have irreducible elements that are not prime. So let's take the example d is z adjoin the square root of -3. So we go back and now we really are in the simplified example of Galian where the norm is going to be a squared plus 3b squared. And I've dropped the absolute value signs because here they're not necessary. A squared plus 3b squared is always non-negative. Now if we take an element of this domain and that element is not 0, 1, or -1, then the norm of that number is at least 3. We can see that by looking at what the norm map is. This also tells us that the units of this domain, D, are just 1 and -1. That's the only time we have a norm of an element equal to 1. Otherwise it's going to be bigger, or 0, unless if the element is 0. So let's take a look at the element 1 plus the square root of -3, which has a norm of 4. And let's try to prove that this element is irreducible using the norm map. So if we take 1 plus the square root of -3, and if we were to write it as x times y, where x and y are elements of this domain, then either the norm of x is the norm of y, which is 2, that's the only way we can factor 4 in a non-trivial way. Otherwise, we're factoring 4 as 1 times 4, and the element that has this norm of 1 must be a unit. So if we are to have if we are to have 1 plus the square root of -3, and if it were going to factor as something, it would either be elements with norm 2 or an element with norm 1, which is a unit. But there aren't any elements with norm 2, And this allows us to conclude that 1 plus the square root of negative 3 is irreducible. Whenever we write it as x times y, 1 of x or y has norm 1, and that means it must be a unit. To see that this element is not prime, so we've taken this element, 1 plus the square root of negative 3, and we've shown that it's irreducible, and now I want to argue that it isn't prime. What we're going to do is we're going to look at the factor ring, d mod the ideal generated by 1 plus the square root of negative 3, and we're going to show that this factor ring is not an integral domain. So let's take a look at the number 2. 2 is certainly an element of the domain, and I want to argue that it does not belong to the ideal generated by 1 plus the square root of negative 3. And I'm going to do this with norm maps as well. So when I take the norm of the element 2, I get the number 4. And I have the same argument going on as I did in the previous paragraph to justify that 2 happens to be irreducible. So because it has norm 4 and nothing in this integral domain has norm 2, and the norm map is multiplicative, we can argue that the norm of 2 is 4. This happens to be the same as the norm of 1 plus the square root of negative 3, and the only units in this ring are 1 and negative 1. When I multiply 1 plus the square root of negative 3 by either of those things, either 1 or negative 1, I certainly don't get 2. And what this means is that 2 does not belong to the ideal generated by 1 plus the square root of negative 3. And so when I look at the coset 2 plus the ideal generated by 1 plus the square root of negative 3, I'm looking at a non-trivial member of the factor ring. However, when I take 2 and I square it, I get 4, and 4 belongs to, well, it belongs to the coset 2 plus ideal generated by 1 plus the square root of negative 3, that quantity squared. It's 2 times 2, so it belongs to the square of that coset, but it also belongs to the ideal generated by 1 plus the square root of negative 3, since I can take 4 and write it as 1 plus square root of negative 3 times 1 minus the square root of negative 3. That shows that when I take the coset, which is non-zero, 2 plus ideal generated by 1 plus the square root of negative 3, and when I multiply it by itself, I end up with the 0 coset in the factor ring. And what that means is I've got a 0 divisor. I have a non-zero member that multiplies by another non-zero member of this factor ring, and I'm getting 0. So when I look in this factor ring, d mod the ideal generated by 1 plus the square root of negative 3, I have 0 divisors, and so I can't possibly have an integral domain. And what this means is that the element that's generating that ideal, 1 plus the square root of negative 3, cannot possibly be a prime element, or the ideal it generates would be prime.